In this lab, I want to take a look at the rolling cylinder on plane joint. I'm going to go back to the assembly environment for a minute, and so we can put a motion rotational translation constraint on here. So we have the rotation about this axis, and let's hide this part for a minute. So I'll turn off the visibility of this part, and we say that this gear turns this rack gear, and so this is a movement along a plane. So the rack is moving along a plane, and it's rotating with the correct ratio, or translating with the correct ratio of the rotation and the translation. Now let's look at some different ways of setting this up, or some different uses of this. In this example, I have put a spring force in between here and here, and then I have put a torque on the shaft of this part. So if I go into that revolution joint and I go to the properties, and I'll go to the second tab, which we haven't used yet, the edit joint torque, and we can see that I put 15,000 Newton millimeters of torque on that. You can also do that as Newton meters, and Inventor will convert it for you, or you can set it up to work in Newton meters. With that torque on this, turning this gear, and then with the spring joints, I'll go to that spring joint and I'll go to the properties of that, and I put a stiffness for that spring of 4 newtons per millimeter. So for each millimeter that this rack goes in this direction, it exerts an additional 4 newtons of force. So if I go 10 millimeters, it puts 40 newtons of force, spring force on here. I also put a damping value so that it doesn't bounce around. Can increase or decrease that damping value. So the free length of this, if I took that spring out of this mechanism, the free length I have set as 75 millimeters. But if I measure this distance from here to here right now, it's actually less than 75 millimeters. I think it's about 74 millimeters. Let's just go ahead and check that. So I'll go to the inspection tab and I'll measure the distance from here to here, and we see that it's 74 point something. So we have already about 1 millimeter of preload on this spring. So 1 millimeter times the stiffness of the spring is our preload, and we can set that to whatever we want by changing the free length of the spring when it's taken out of the mechanism. It's already partially compressed. So I'll go ahead and play this, and the torque is going to turn that gear, and at some point this is going to come in contact and it can't turn any further. Now the mathematics for this might be fairly simple to calculate, but let's increase that spring a little bit more. So I'm going to go to the properties of the spring, so we could either experiment with the properties of the torque on the input, or we might change the spring force. Now keep in mind, this is a spring force. That force could represent something that's being pressed in between here and here. Just think of it as the force, maybe not as the physical spring that we get a representation of. I'll play this again. And so with that spring a little bit stiffer, with the torque that's input here, it doesn't push this all the way to that block. And of course we can display on the output grapher, we can display with the torque that I imparted with this red gear, have a force of about 302 newtons being applied continuously. That's the torque on this shaft. And then for the spring, as it compresses, let's zoom in on this. So I'll zoom in on this area, and so with 1 millimeter of the preload, I have about 4 newtons of force to begin with. And then if you click inside this graph and you hit the left and right arrow keys, you can see how that force is changing. And so as it compresses, it increases. And then when the model gets to about where it is stabilized, we see this curve flattens out. Now I'm showing this force as a negative number. If you want to show it as a positive number, if I right click on this and I go to curve properties, and I'm going to put an active multiplier of -1 times that force, And that would just flip our graph so that we display both of these forces in a positive number. So this curve is the torque on the shaft of this gear, and then this curve is the force of the spring, or the spring force. I keep want to emphasizing that that is a spring force, not necessarily a physical spring. Well, we can see how we can start to get information from the properties of our analysis from the output grapher. Now sometimes we can hone in on a value that we're interested in more quickly by trial and error than we could by doing a hand calculation. So we could put what we think is a maximum value, then put in a minimum value, and then by trial and error go halfway in between those values until we hone into the information that we're interested in. For example, maybe where these two curves converge. With the rolling cylinder, think of this as any cylinder rolling on any plane, so we don't necessarily have to have the teeth on here. And so in this case, the blue part is grounded in position and the yellow part rolls along the grounded part. Now let's go to the View tab and I'll turn on the construction surfaces. And so really the only thing that was needed was this planar surface and this surface cylinder to set this up. So even though that there are teeth on this, ignore the teeth for a few minutes and just think of anything, for example, a car tire rolling along a plane and not sliding. Don't step on the gas too hard or the brake too hard, and that wheel or that cylinder rolls, not sliding, rolls along the plane. So let's look at how to set all this up. I'm going to put a link to where you can find the files for the Arbor Press. They are in the Inventor tutorial file data set, and if I go to this folder, Next Steps, and I'll go to Tutorial Files, and I'll go to Arbor Press, and I'll select the Arbor Press assembly. So again, I'll put the link to where you can get these files in the description of the lab. So if I look in the relationships folder, somewhere in here there is a rotational translation constraint that defines the ratio between the ram or the rack gear and the pinion gear. And let's see if I can find that, because I don't see it over here. So I'll go to Find in Browser, and here's the ram. If I expand that, so here's that rotational translation constraint. And if I go to the properties of that or edit that, we see that it's 3.142, and if you recognize that number, in fact I probably would have just put this in as pi, and I see that that's red. If I put it in as pi times 1, it'll carry it out to whatever number of decimal places that the computer calculates. We're going to see that the pitch diameter of this pinion gear is 1 inch. The diameter is 1 inch, so times pi gives us the circumference of that pitch circle. And I'm going to turn off the visibility of this part, and I'll turn off the visibility of this part. I may turn off the visibility of this part as well. Alright, so if I drag this, we see the motion. Now that kinematic motion though doesn't give us any indication of forces, so we have to get a rolling cylinder on plane joint in order to calculate forces in dynamic simulation. If I go to the dynamic simulation environment, I have a prismatic joint. This can only move in 1 degree of freedom straight line translation, and then a revolution joint for this part, and I'm not sure why there's 2 revolution joints there. We can drill down actually and find out. So that's the shaft to the arbor frame, and then this was the collar, so the collar going around that shaft. And actually that one could be removed. Let's right click on this, and I'm going to edit that insert, and I'm going to tell it to lock the rotation of that insert. And so now there's just 1 revolution joint there. Let's make sure that this still works. So go back to the assembly environment, and it still works. If the teeth aren't lined up, if you go to that rotational translation constraint and temporarily suppress it, and then I will line this up, and I'm just going to line it up by eye, and then I will right click and unsuppress that. We see that now it stays lined up. I'm going to open up the pinion shaft, and somewhere on here we should have a circle for the pitch diameter. I'm going to edit to sketch 1. Now I see actually that sketch isn't fully defined. Let's try adding a collinear constraint between this line and this line, and it doesn't want to do that. Let's just try dragging something and see if we can figure out what we need to do on that. So instead, let's make this line tangent to this arc. So I'll do tangent this line to this arc, and then that works, and now it's fully constrained. Something fishy about this line right here isn't set up right. I'm not going to take the time to drill down and find why that became an issue. I might just see if I can just delete that line. So I can delete those two lines and everything is still fully defined. The reason I came in here was to find the pitch diameter, and so if I find this dimension, it shows me that the pitch diameter is this circle right here. So this is the addendum, this is the pitch diameter, and then this is the root circle, and then this is the base circle if you're familiar with modeling gears. So the second one in, that is the pitch diameter. So I'm going to make that sketch visible. I exited out of the sketch, I'll make it visible. I'm going to start a new sketch on the face of this part, and I'll project geometry, that pitch diameter. I'll then hide sketch 1, and I will change this to an object line. And again, if we measure that, if I go to the inspection tab and I set this to all decimals, we see that that is 25.4 millimeters or 1 inch in diameter. Let's put this on dual units. Okay, so 25.4 or 1 inch in diameter. And then I'm going to extrude that, but I don't want to add any mass to this part, so I'll extrude that as a surface body. So I'll change it to surface body, and I'm going to tell it to go TO2 up to, say, this point right here. So it's going to extrude that as a surface back to there. That distance really doesn't matter, just so that we have that cylinder. I'll save this file and I'll go back to the assembly. So that gives us the pitch diameter for the pinion. Now we need the surface where this circle would be tangent to the surface going through the ram. So I'll go to the inspection tab and I'm going to do measure, and I'm going to put it on all decimals, and I'm going to do dual units, inch and millimeters. And so then I'm going to make sure my selection priority is on faces and edges. I'll select this cylinder, and then I need to select the back face of this ram. Now actually I guess I could select the face up here on front, but I'm going to do the back face. And then I want to know what that minimum distance is between this cylinder and that back face. So if I come here and click on this where it says minimum distance, it shows me then what that minimum distance is, and I'll copy this to the clipboard. Notice this is in inches, and if I show it in dual units, millimeters, this is in millimeters. I'm going to copy this to the clipboard, so I'll do copy, and then I'll close this file and I'll open up the RAM, and then I'm going to create a plane, and I'm going to offset it from this back face, that's where we took our measurement, as minus Control V, the number from the clipboard, and I'll say OK to that. So that puts our plane in here where that cylinder will be tangent to it. I'll save this, I'll close that. Now there may have actually been a plane already in there. Let's go ahead, let's go back and open that up, and I'm just curious to see if there was a plane in there already. No, so we had to create that plane. And sometimes I'll create that as a surface body rather than as a plane, depending on what I'm doing, either way in this case. Alright, so then I'll go to dynamic simulation. Let's go ahead and save this first. And so I'll go to the environments, dynamic simulation, and then I'm going to add my rolling cylinder on plane, and it asks me to select a plane. Actually I have to say OK to this, and then I can select the plane, and then I will select the cylinder, and now before I say OK to that, if I say OK right now, it will give me an error because we don't need to add the tangency. These two components are already tangent. So I'll put it on one constraint rolling. I'll say OK to that. Then if I drag this, we see that it now rotates correctly. Now I saw that if I come down here too far, that this part goes through this table, so I may want to add a constraint for that. Or I might put some object in between here that I am actually using this press to press one object into another. So let's go ahead and do a 3D contact. Now I could either do this as 2D or 3D. I don't have a face to use as the 2D, so I'll do a 3D contact between this component and this component. And now when I drag this down, it stops when it comes in contact with that table. So in later labs we will see how to add a force along different lengths of this handle, and so we'll see what the moment the torque is rotating around this shaft depending on where we put our hand along this handle. I'll turn on the visibility of the frame again. You stayed to the end of the video. Let me show you some bonus tips. So let's say you go to open up a part or an assembly and the preview is not in the best orientation. So I'll go ahead and open this file, and we've seen that we can change what is referred to as the top on our view cube. So I'm going to rotate that around and I'll set that as the top view, and then I'm going to rotate around to, let's say I want it to always open up like this, or I want that to be my home position, so I'm going to set that as my home position. But that doesn't change the view when we go to open it. We still see it's laying on its side. Now when we open it, it will open up like this now, but let's look at how to change that thumbnail. So I'm going to right click on the top node and I'll go to iProperties and I'll go to Save, and first I set this in the view how I want it. I probably ought to turn off that work plane, but I'll tell it to capture the image from the active window, or we could import an image that we have captured separately, and then I'll say apply to that. Let me save it. Now when I go to open this, I see that it is oriented in a more logical orientation. Now we can also do that when you're saving it. So on your initial save, I'm going to do save as because it's already been saved. You can click on options and you can set that option of how to save the thumbnail to capture the current view when you save the initial file.